students, greetings of the day. Today I am going to discuss few numerical problems based on the concept of center of mass and its motion. This is very important from your examination point of view as well. Every year you get one or two questions based on this concept. So why waiting then? Shall we start?
Let's start practicing the problems. Here all the questions are either from location of center of mass or motion of center of mass. So let's start with the first one. Half of the rectangular plate shown in figure is made of a material of density ρ1 and the other half of density ρ2. The length of plate is L. Locate center of mass of the plate. Here it is not given that with respect to which point we have to locate the center of mass. So let us consider that reference according to our convenience. Let us consider that reference to be the point O. So if we write now XCM with respect to point O I am writing. So it should be equal to, now we have to write mass of this left plate. If we consider density, since density is given here ρ1, so the mass can be written as K ρ1 into L by 4 because C1 has coordinate L by 4 plus K ρ2 3L by 4 which is x coordinate of point C2. Here I have written K as area of both the parts and them being equal. We can simply replace this area by a constant that is equal to K. Here I have multiplied density with K, that K can be written as area of left half as well as the right half because these are having the same area. So simply I have written K in place of area and this should be divided with whole the mass and that is equal to K ρ1 plus K ρ2. Now if I solve this, finally I will get ρ1 plus 3 ρ2, 4 taken common here, it will be ρ1 plus ρ2 whole multiplied with L. This is location of XCM with respect to the point O we have considered here. As we can see, it is symmetric about x-axis, so of course YCM has to be 0. Directly we can write from the symmetry condition, as I had told earlier also, that if a shape is symmetric about x-axis then its YCM will be 0 and vice versa. So we got x and y coordinates of its center of mass. Next is the question. The density of a linear rod of length L varies as, here density is not constant, it is varying with x, that is given by a plus bx. So let us consider a rod of length L which has this varying density where x is distance from the left end. So if we consider this to be the reference, from here let us consider a small element at distance x and this element is having width dx. Now we have to write center of mass. Of course it has to be along the x-axis, so XCM can be written as, now we have to write, since this is a continuous mass distribution, so we have to write x multiplied with dm upon the whole mass, that will be integration of dm. So let us now substitute the values. dm can be written as density multiplied with length. Density here is given as linear density, so directly it can be written x multiplied with a plus bx into dx. X has to vary from 0 to L and again in denominator we have to integrate. Here directly we cannot write value m because it is having a varying density, so we have to integrate density into length to get the whole mass, that is a plus bx multiplied with dx. This integration also is from 0 to L. On integrating the numerator and the denominator, the result can be written as a L square by 2 plus b L cube by 3 upon a L plus b L square by 2, which on further solving will be equal to 3al plus 2bl square upon 3 taken common 2a plus bl. This is the location of center of mass with respect to the leftmost point. Let's move to next question. A cubical block of ice of mass m and edge L is placed in a large tray of mass m. If the ice melts, how far does the center of mass of the system ice plus tray come down? Here it is asking for how much the center of mass will be displaced. So it is something from motion of center of mass. Now we have come to that part. So let us see how to solve this question. Let us consider this being our tray, and inside the tray a cube of ice is put here. Of course its center of mass will be at the center of cube. So if we write our origin to be here, which is just below the center of cube at a distance x1 from the tray. So we can write x for center of mass for the system to be equal to m. This I am writing for cubical block of ice, so it has to be m. x2, this x2 is location of center of ice cube with respect to O. So let us draw this also in your figure, that is equal to x2. Now we got mx2 plus capital M, which is for the tray, multiplied with x1 upon the whole mass, that is equal to m plus m. This is location of center of mass of the whole system with respect to the considered origin. Now when the ice melts, the water of mass small m will spread on surface of the tray, and as the tray is large, the height of water almost will be negligible. So then we can say that center of mass of water will be on the surface of tray, which is at a distance x2 minus L by 2 above the origin. If we now consider the new center of mass of the ice tray system, which is at a height x dash, then x dash can be written as m. It will be x2 minus L by 2, because initially the edge is L, and if this center has come to the surface of tray, so of course it has come down by L by 2. So we can write its location as x2 minus L by 2 plus mx1 for tray, it's not going to change, upon the whole mass m plus m. So now we can write shift to be equal to x minus x dashed, and on subtracting the values written here, we will get this to be equal to ml upon 2 m plus m. So by this value, the system ice plus tray will have its center of mass lowered when ice has been melted. In this question, consider a two-particle system with the particles having masses m1 and m2. If the first particle is pushed towards the center of mass through a distance d, by what distance should the second particle be moved so as to keep the center of mass at the same position? Now here let us consider initially the masses were, this is m1, this is m2, and let this be the center of mass. We are not knowing its location, but let us consider this be the center of mass, which is at a distance x1 from m1 and x2 from m2. Now since the mass m1 has been moved towards C by a distance of d, so we have to see by what distance m2 will have to move, so that center of mass has to be in the same position. So let us consider that m2 has to move by distance, let this be d dashed, towards center of mass. Now we have to write position of center of mass to be the same. So of course we will write m1 x1 to be equal to m2 x2, then only center of mass will remain at the same position, because the product of mass into displacement of first particle should cancel out the product of mass and displacement of second particle. And for the new condition, we can write m1 x1 minus d to be equal to m2 x2 minus d dashed. These two equations have to be satisfied if center of mass has to be at the same position. So if we now solve these two equations, the final result will be m1d to be equal to m2d dashed. From here we can write d dashed to be equal to m1 upon m2 multiplied with d. So by this distance, second mass m2 has to be pushed towards center of mass so that c can remain at its initial position. Now here you can see one more question is there where a number of forces are acting on the given system. A body of mass 2.5 kg is subjected to the forces as shown here, and we have to calculate acceleration of center of mass. As we all know, acceleration of center of mass can be written as summation of all the forces upon mass of the whole system. So we will simply apply this to get acceleration of the center of mass. But of course here, since all the forces are in different directions, so we have to write this in projection form along x-axis and along y-axis. So now we can write ax to be equal to all the forces we have to write along the x direction, and these will be 4 cos 60 minus 6 plus 6 cos 53 degree plus 5 cos 37 degree. These are all the forces in x direction, whole divided by mass, which is given here 2.5 kg. This will come out to be 3.6 all the forces along x-axis upon 2.5. If I write along y direction, then it has to be along y direction forces are 4 sin 60 degree. There is no component for 6 Newton force plus 5 sin 37 degree minus 6 sin 53 degree, as it will be in downward direction. So these are the forces along y-axis, and this whole divided by 2.5, that is equal to 1.7 upon 2.5, and then we will get ACM to be equal to ax square plus ay square. If I substitute both the values numerically and then square, add, the result will be 4 upon 2.5, which on calculation will be equal to 1.6 meter per second square. But as we know, acceleration is a vector term, so there must be specification of direction as well. Directly from here it can be written tan theta to be equal to, where theta is angle between horizontal and the whole acceleration, that will be equal to ay upon ax, which is 0.47. So we got the acceleration both in its magnitude and the direction. This is very common question here. As you can see, a projectile is fired at a speed of 100 meter per second at angle 37 degree above the horizontal. At the highest point, the projectile breaks into two parts of mass ratio 1:3, the smaller part coming to rest. Find the distance from the launching point to the point where the heavier piece lands. As you can see here, this is the point where the heavier piece has landed. So we have to write this distance from here, and since the lighter mass had been come to rest, so it simply fall freely and came vertically to this point. Now let us solve this question. See, here it is saying that at the highest point the projectile has been broken. So at this point its velocity has to be horizontal, and now lighter part has come to rest. So the heavier part of course will move with increased horizontal velocity. From momentum conservation we can say this. In vertical direction, both parts will be having zero velocity, because here at maximum point the velocity is along horizontal. So for both particles, lighter and the heavier one, vertical component has to be 0, and they have same acceleration also in vertical direction. So they will cover equal vertical displacement in a given time, and both will hit the ground together. As internal forces do not affect the motion of center of mass, the center of mass will hit the ground at the position where the original projectile would have landed, which is this position shown here. The range of original projectile, as you know, can be written as, that will be the center of mass. It has to be 2u square sin theta cos theta upon g. If I substitute all the values, that will come out to be 2 into 10 to the power 4. Theta is given 37 degree. So 3 by 5 into 4 by 5 upon 10. On solving, it will come out to be 960 meter. What this distance is? from launching point to the range of original projectile motion that we got to be equal to 960 meter. This will be the position of center of mass. Now since smaller block has come to rest, it will fall down vertically and will hit the ground here, which is at half the range, and this value is equal to 480 meter. So of course heavier block has to hit the ground, so that we can write for center of mass, which is 960 meter, it should be equal to, the masses have ratio 1:3, so the lighter part will be have mass m by 4, and we can write m by 4 into 480 plus 3m by 4 into x2. x2 I have taken as this position for the heavier mass, its coordinate from the launching point, and this whole divided by m. Now on substituting all the values, x2 will come out to be 1120 meter. This is the point at which the heavier mass will land on the ground. The next question is, a block of mass m is placed on top of a bigger block of mass 10m. As shown here, all the surfaces are frictionless and the system is released from rest. Find the distance moved by the bigger block at the instant the smaller block reaches the ground. Here the surfaces are frictionless, so no friction is acting, and the forces between m and 10m are the only forces that is responsible for any displacement along horizontal direction, because as we know, gravity is in vertical direction, so it cannot displace the system in horizontal direction. Only the normal is the force between the surfaces which is responsible if there is any displacement along x direction, and as normal is the internal force for the masses m and 10m, so if we write for the whole system that is consisting of m and 10m, delta xcm can be written to be equal to 0 because there is no external force in horizontal direction. And let us write, when it has come, block m has come to this point, the distance it has travelled with respect to which in horizontal direction is 2.2. So let us consider, if displacement of 10m is by x towards right, so we can write delta xcm to be 0. That will imply m, this has to be displacement of m with respect to 10m, that is 2.2, plus displacement of 10m, that is minus x because it is in opposite direction, and this has to be equal to 10mx because delta xcm has to be 0. On solving this, we will get x to be equal to 0.2 meter. So the bigger block moved by distance 0.2 meter at the moment block m comes to the lowermost point of wedge. Move to the next question now. The hero of a stunt film fires 50-gram bullets from a machine gun, each at a speed of 1 km per second. If he fires 20 bullets in 4 seconds, what average force does he exert against the machine gun during this period? This is something related to change in momentum. Now if we write momentum of each bullet, it can be written as, for each bullet first I am writing, so that P can be written as 0.05, this is mass of bullet in kilogram, multiplied with its speed, that is 1 km per second, so has to be multiplied with 1000, that is equal to 50 kg meter per second. This is momentum of each bullet. So the gun is imparted this much of momentum by each bullet fired. Thus the rate of change of momentum for the gun is, since it is firing 20 bullets in 4 seconds, so it has to be multiplied with 20. Then we have to write momentum of each bullet upon the time, that is 4 seconds. On solving, it will come out to be 250 Newton. This is the force that is applied on the gun. And if the stuntman has to hold the gun, he must exert a force of 250 Newton against the gun. So this must be the same force written here. One more question. A block moving horizontally on a smooth surface with a speed 20 meter per second bursts into two equal parts continuing in the same direction. If one of the parts move at 30 meter per second, with what speed does the second part move, and what is the fractional change in the kinetic energy? Here, as there is no external force on the block and only internal forces are responsible for breaking up of block in two parts, so we can write linear momentum of block before and after the break to be equal. So let us write this. As it has been burst into equal parts, so I am writing initial momentum m into 20 to be equal to m by 2. One of the part is moving with 30 meter per second, so multiplied with 30, and for the remaining part, that is m by 2, let the speed be v. On solving this, v will come out to be 10 meter per second. So now we can write change in kinetic energy will be equal to final kinetic energy minus initial kinetic energy. So it will be half m by 2 30 square plus half m by 2 10 square minus half m 20 square, and on solving it will come out to be 50 m meter square per second square. But it is asking for fractional change in kinetic energy, so it has to be divided with initial energy. So we can write delta Ke upon Ke initial, that will be equal to 50 m upon the initial energy, which is half m into square of 20. These two got cancelled and the final result will be equal to 1 by 4. So this is the fractional change in kinetic energy. Let us solve one example. A wagon of 200 kg is moving on a smooth track with velocity of 2 meter per second. A man of 80 kg also runs in the wagon with a velocity such that speed of the center of mass of the system is 0. Find the velocity of man relative to the wagon. Here we have to calculate relative velocity of man with respect to wagon. If we write velocity of center of mass for the system, by definition it can be written as velocity of center of mass to be equal to mass of wagon multiplied with velocity of wagon plus mass of man multiplied with velocity of man, and this whole being divided by mass of wagon plus mass of man, that is mass of the whole system. On substituting all numerical values, it will be 200 into 2 plus 80v. Here we have assumed velocity of man to be v. So this divided by, now mass of both has to be written, it is 280. And this has to be equal to 0 because there is no external force on the system. So velocity of center of mass, if initially it was at rest, it has to be at rest even after this event. And velocity of center of mass we have to write to be equal to 0. On solving this, we will get v to be minus 5 meter per second. This is velocity of the man. And now with definition of relative velocity, we can write velocity of man to be equal to velocity of man with respect to wagon plus velocity of wagon. Here we are related in this term, which is velocity of man with respect to wagon. So its value will be Vmw. We can write as Vm minus Vw. On substituting the values, this will be equal to minus 5. We have just now obtained, that is velocity of mass minus velocity of wagon, which is given here 2 meter per second. So minus 2, and the final result is minus 7 meter per second. Here this minus sign is indicative of direction, but only we have to write its magnitude. So the correct option will be option number C. In next question, a car of mass m is moving with a uniform velocity v on a horizontal road. When the hero of a Hindi film, again the hero has come, drops himself on it from above. Please do not practice this at home. Taking the mass of the hero to be m, what will be the velocity of the car after the event? Now here if we consider initial momentum for the hero in horizontal direction has to be equal to 0. So for the whole system, if we write initial momentum in horizontal direction, that will be equal to mv, that is momentum for the car, and it will be towards right because the car is moving towards right. Finally, the hero is sticking to the roof of the car, so they are moving with, of course, equal horizontal velocity. Let that velocity be v dashed, and we can write final horizontal momentum to be equal to m plus m, both are moving with the same speed, v dashed. On equating these two, we will get mv to be equal to m plus m v dashed being mv upon m plus m. So this is the velocity with which the both will move as a whole system in horizontal direction. Today we have solved so many questions related to center of mass. Even this momentum conservation is also related to center of mass, because if no external force is acting on the system, then its momentum has to be conserved, and center of mass also must be at the same state of motion after the event as it was before the event. So with this, now our practicing of numerical is over. Let us see forward to the next session. Bye.